Welcome back to The Deep Dive. We're the show that helps you get beyond the headlines, really understand the complex stuff. Today, we're tackling something interesting about car safety. You know, when you think about a car being safe, what usually springs to mind?
Crash tests, probably. Airbags. Maybe fancy braking systems.
Exactly. Things related to the design, the engineering up front. We kind of assume safety is all locked in when the car rolls off the factory floor.
Right. Like, it's done. Finished.
But what if that's... Well, what if that's just the beginning? What if the real test of a car's functional safety starts after it leaves the factory?
Now you're getting to the heart of it.
What if safety is less of a sprint to the finish line of production and more like a marathon that lasts the car's entire life?
That is absolutely the core of what we're digging into today. Functional safety isn't, static. It's not a box you just tick once.
It's alive, almost. Exactly. It's dynamic. An ongoing commitment. It stretches across the entire lifespan of that vehicle, from the moment its bits and pieces are made through every single mile driven, every time it goes in for service, and even right up until it's retired, taken off the road for good.
So today we're doing a deep dive into part of the big automotive safety standard, ISO26262, that maybe doesn't get as much attention.
That's right. We're focusing on ISO26262-Part specifically Part 7, and its title tells you everything. Production, operation, service, and decommissioning phases.
Okay.
This is where we see how safety is actively maintained, how it's ensured throughout that whole life cycle, how it's built, how it's used, how it's fixed, even how it's, eventually taken apart. It's all about making sure those safety goals set way back in the design phase, they actually hold up continuously in the real world. Got it. So our mission today is pretty clear then. We're going to unpack these phases: production, operation, service, decommissioning. We want to show you how vital they are, how they contribute to keeping vehicles safe long after they're designed. It's about seeing safety as this complete cradle-to-grave thing.
Precisely. A much bigger picture.
Okay, so let's set the stage a bit. Many of our listeners will know about the V model in development, right? From earlier parts of ISO 26262.
The classic V concept, requirements, down to hardware, software, then testing back up.
Right, that whole meticulous process of design, build, test, verify, it's rigorous.
Extremely.
But you're saying Part 7 kicks in right where that V model kind of hands off.
Exactly. It picks up at that precise moment, the transition from the blueprint, the theoretical design, to the actual physical product hitting the assembly line, and then eventually the road.
So it's the bridge from design to reality.
It is. And it's the start of that long marathon we talked about, where all those safety designs meet the real messy world.
And that transition, that handover, it sounds absolutely crucial.
Oh, it's vital, because functional safety just isn't static. It can't be. You design it, yes, but new risks, they can pop up anywhere after that.
Like where? During manufacturing?
Definitely during manufacturing.
Yeah.
If certain safety-critical characteristics aren't controlled with extreme precision, you can accidentally build defects into the system. Then think about when the car's being driven. Normal wear and tear, weather, maybe some component just degrades unexpectedly.
Right, things just happen over time.
Exactly. And safety functions can get compromised. Or what about service? A mechanic makes a mistake, uses the wrong part, maybe uploads the wrong software update.
Ooh, yeah, that could be bad.
Very bad. It could seriously undermine all that careful safety engineering. And even at the very end, decommissioning, taking the car apart, bad handling, can cause hazards.
So Part 7 is trying to manage all that potential risk after the design is done.
Precisely. The main goal, stated right there in Clause 5.1, is to make sure functional safety is achieved and maintained throughout the vehicle's entire life, not just development. And it's focused, importantly, on hazards from malfunctioning behavior of the electrical and electronic systems.
Okay, so not necessarily like a fire caused by a fuel leak, unless that leak was triggered by an EE system failing.
Exactly. It's about the intelligent systems misbehaving in a way that causes harm. That's the domain of functional safety here.
That distinction really matters. It shows it's not enough to design it safe. You have to build it safe and keep it safe. So let's zero in on that first step after design. Production, the factory floor. How do you make absolutely sure that a perfectly designed safety feature isn't messed up when it's actually being put together?
Right. How do you translate that design intent into reality? That's Clause 6 territory, the production phase. The objective is crystal clear. Ensure functional safety during production after the design's been released.
And it's more than just general quality control.
Oh, much more. Quality is fundamental, of course. But this is laser-focused on the specific things in manufacturing that could impact the safety functions meeting their goals. And it starts, really has to start, with planning for production. That's Clause 5.4.1. You don't just start building, you plan how to build safely.
What goes into that plan?
Several key things. First, detailed production requirements. These aren't vague. Think specific assembly instructions, maybe exact calibration steps for a critical sensor in an ADS system, or strict adherence to standards like IPC for circuit board manufacturing, making sure the foundation is reliable.
Okay, very specific instructions. What else?
Something really critical. Identifying safety-related special characteristics.
Special characteristics. What are those?
Think of them as the crucial parameters, the DNA of the product's safety. If these aren't controlled precisely during manufacturing, safety could be compromised instantly.
Can you give an example?
Sure, like the exact temperature profile during soldering for an ECU. Too hot, too cold, too fast, you get bad joints, potential failures later. That's a direct safety impact.
Ah, okay.
Or the precise torque for tightening bolts in the steering system.
Yeah.
Not tight enough. It could loosen. Too tight. Maybe you damage something. Both are safety risks. It also covers things like exact material properties for parts, really tight production tolerances, making sure the right configuration of components is used. Even tiny variations matter here.
So it's about incredible precision, not just getting the right part, but handling it exactly right.
Exactly right. Which leads to the next point. Planning for the handling and management of elements.
Elements meaning parts, software.
Both. Hardware parts might have a limited shelf life before they degrade, so you need to manage storage time. And, maybe even more critical, ensuring the correct software version and the correct calibration data gets loaded onto the ECUs.
Yeah, you wouldn't want the wrong software on a brake controller.
Absolutely not. Imagine an older version without a crucial safety patch, or software meant for a different vehicle model.
Yeah.
Catastrophic potential.
Well, how do they prevent that?
The standards suggest practical things. Using checksums to verify the software and data after loading. Reading back part numbers or calibration IDs from the ECU, and checking them against the specific build sheet for that exact vehicle.
Right, multiple checks.
These are safety gates, really. Non-negotiable steps.
And what about the people doing the work?
Huge factor.
Yeah.
Personnel competence. The skills, the training, the experience of the workers on the line are vital. Well-trained people make fewer errors. All of this gets documented in the production plan. It's a detailed blueprint for manufacturing. Process flow, work instructions.
Even for fixing things, like rework.
Yes, detailed instructions for rework, though often with strict limits for safety-critical items. Maybe only allowing rework on simple connections, like components with 3 pins or fewer. The plan also specifies the tools, the equipment, and crucially, traceability measures. Labeling parts so you can track them.
That seems thorough. But what about anticipating problems before they happen?
Excellent point. That's a core part of the planning, too. Anticipating failures. The standard requires identifying reasonably foreseeable production process failures.
How do they do that?
A common method is PFMEA, process failure modes and effects analysis. Engineers basically brainstorm all the ways the production process could go wrong. Then they figure out the potential impact on safety for each failure mode, and then they implement controls to prevent it or mitigate the effect. It's proactive.
So key F&EA feeds into the actual controls on the line.
Directly. It informs the production control plan. This plan details the specific checks, the sequence, the methods, the test equipment, the pass-fail criteria, everything needed to ensure those special characteristics are met during production.
Okay. And is there feedback? If they find something tricky to build safely, does that go back to the designers?
Yes. That's the producibility requirements feedback loop. If production planning reveals, say, a connector design that's easy to install incorrectly, that feedback goes back to development. Maybe they add a poka-yoke feature mistake proofing, making it physically impossible to plug it in wrong.
Clever. Engineering out the potential for error.
Exactly. And even before full-scale production, there's the pre-production phase, Clause 5.4.2. This is where they fine-tune the process on a smaller scale. They analyze any differences between this pre-production setup and the final planned series production to make absolutely sure the process is capable of delivering the required safety consistently at volume.
Wow. The level of planning before a single production car is built is intense, really detailed.
It has to be.
But okay, the planning's done, the lines are rolling, machines are running, people are working. How does Part 7 make sure all that meticulous planning actually happens consistently day in, day out?
Right, that's the execution phase of production, covered in Clause 6.4.1. This is where the rubber meets the road, so to speak, on the factory floor. The fundamental rule is implement the production process and controls exactly as planned and maintain them rigorously. That includes ongoing training for everyone involved. Keep skills sharp.
So it's not set and forget.
Definitely not. There's a huge emphasis on continuous analysis and measures. You're constantly monitoring the process, looking for any deviations in those safety-related special characteristics.
And if you find something,
You identify the process failure, figure out the potential safety impact, and then implement and verify corrective measures immediately. That might mean adding extra checks, sorting parts, maybe reprocessing things, or even swapping out components if they don't meet the standard. It's a real-time correction loop.
And what about the machines and tools themselves?
That's covered by ongoing capability evaluation. You have to continually evaluate and maintain the capability of the process, the equipment, the tools, the test gear, everything specifically regarding functional safety. Are the machines still holding tolerances? Are the test rigs accurate? This often links to quality systems like IATF 16949, which mandates control of monitoring and measuring equipment. The calibrated torque wrenches, validated sensor testers.
I see. Quality underpinning safety.
Absolutely. And then there's strict adherence to controls. Every check specified in the production control plan must be done. No cutting corners.
And documented.
Meticulously documented.
Yeah.
Control date, what was checked, maybe by VIN or serial number, the result, pass, fail, or actual measurement data, compared against the limits. It creates that crucial audit trail. Accountability.
Okay. And one last thing for production. What about changes? Can they just decide to use a slightly different part one day?
No way. That's configuration control. Only the approved configurations, the exact parts and software defined in the release documents, can be produced. Any deviation, any change at all, needs formal authorization from the responsible people. It's a strict gate to prevent unauthorized changes sneaking in and causing safety issues.
It really paints a picture of safety being built in, verified, and controlled at every single step on the line. Amazing. But okay, the car's built, it passes all the checks, it rolls out the door. Now it's out in the real world, in the hands of a driver. How does functional safety stay alive and kicking for the next 10, 15, 20 years? Through heat, cold, rain, bumps, maybe questionable maintenance?
Now we move into the next major section, Clause 7, covering operations, service, and decommissioning. The goal here is simple to state, complex to achieve. Maintain functional safety throughout the rest of the vehicle's life.
So more planning involved here too.
Oh yes, extensive planning. Planning for operation, service, and decommissioning is in Clause 5.4.3. It's incredibly broad. You're defining requirements for maintenance, for repairs. You're figuring out what the user needs to know for safe operation that goes into the user manual. You're planning for decommissioning way down the line, even planning information for emergency rescue services. And defining the vehicle's warning and degradation strategy, how it tells the driver something's wrong and what it does about it. And critically, this planning sets up the framework for field monitoring. We'll definitely circle back to that. It's huge.
Okay. Does handling parts and software matter here too, like in production?
Absolutely. Handling of elements is still key. Planning safe storage times for spare parts so they don't degrade on the shelf. Specifying the exact procedure for flashing new software onto an ECU during service.
Right, ensuring the mechanic uses the correct, validated version.
Precisely. Preventing software errors introduced during maintenance.
Oh.
All this feeds into the service plan.
What's in that?
It details the maintenance activities, the required intervals, like maybe a sensor needs recalibrating every 2 years, and the specific tools needed. And building on that are the service instructions. These are the real nitty-gritty details for the technicians.
Step-by-step guides.
Exactly. Detailed procedures, methods, work steps, diagnostic routines, required tools like special calibration rigs, and crucially, control steps to verify safety characteristics after the service is done.
So, proof that the repair actually restored safety.
Yes. Ensuring the function is back to its safe state. The instructions also cover traceability, tracking parts, and software versions used in service. Service tools might even enforce loading the correct software. It also includes important info on, say, when it might be permissible to temporarily deactivate a function for service, how that changes the vehicle, and critically, how the driver must be informed about that change.
That level of detail for service is impressive. It ensures the safety integrity isn't lost in the workshop. But what about the driver? You mentioned the user manual. Let's be honest, most people probably glance at it once, if that. Is it really a safety document?
According to ISO 26262, absolutely.
Yeah.
The standard considers user information, the manual, a critical safety document. It's not optional reading, it's part of the safety concept.
Really? What does it have to include?
A lot. Clear descriptions of the safety functions, how to use them correctly, their status, different operating modes. It must tell the driver what actions they need to take to maintain control if a failure occurs, especially if the car's warning system activates. What does that light mean, and what should you do right now?
Okay, that's important.
It also needs to specify what service actions the customer might need to take if there's a failure warning. When do you need to pull over safely and call for help? And here's something interesting. It must include warnings about hazards from interactions with third-party products.
Like what?
The standard gives the example of a tow hitch blocking a parking sensor. The manual needs to warn you that your parking assist might not work correctly with a trailer attached. You can't rely on it blindly in that situation.
Preventing misuse based on assumptions?
Exactly. And maybe even more important for new tech, warnings about proper use of novel safety functions to prevent misunderstanding. Think about automatic parking brakes versus manual ones. If you don't understand how the automatic one engages or disengages, you could accidentally let the car roll away. The manual has to bridge that knowledge gap. Clear communication is vital for safety.
That really reframes the user manual. It's not just features, it's active safety information. User education as a safety layer.
Precisely.
And like production, is there a feedback loop here? Do problems found out on the road or in the workshop get back to the designers?
Yes, definitely. Feedback to development is built in. If planning or real-world experience shows a need, maybe diagnostics are difficult in the field, that goes back to the design teams. The standard mentions adding an error logging function to an ECU based on service feedback, making future diagnosis much easier. It's continuous improvement.
Makes sense. And you mentioned rescue services.
Yes, rescue services information, providing clear instructions and warnings for first responders, how to safely disable airbags before cutting into a car, or how to handle the high-voltage systems in an EV during an emergency, protecting the rescuers.
Okay, so the planning covers everything from the driver's manual to the tow truck driver. Now, the car is out there living its life. What happens in the execution phase? Day-to-day driving, service visits, unexpected issues?
Right, this is execution of operation, service, and decommissioning under 7.4.1. This is where the plans meet reality. And the absolute cornerstone here is the field monitoring process, clause 7.4.1.1. This is critical for ongoing real-world safety.
Field monitoring, so watching how the cars perform out there.
Essentially, yes, but it's systematic. Collecting and analyzing data from the field, from vehicles, dealerships, maybe even incident reports, specifically looking for potential safety issues.
What kind of issues?
Things that maybe weren't caught in testing. Unexpected failure modes, maybe a software bug that only shows up under rare conditions, higher than expected failure rates for a component.
And the goal is to spot these patterns.
Exactly. Spot patterns, analyze the root cause, and critically trigger action. This isn't just data collection for its own sake. The analysis has to lead to decisions. Maybe it's a service bulletin, maybe an over-the-air software fix, or in serious cases, a recall.
So this is how recalls happen, based on real-world data indicating a safety problem.
It's a major input, yes. This process ensures that emerging safety issues identified after launch are actually addressed.
That sounds like a powerful feedback loop. Does this data have other uses? Can it, prove a component is safe if it performs well for years?
You've hit on a really interesting aspect, the proven in use argument. That references Part 8 of the standard, Clause 14. If you have extensive positive field data showing a component or system has performed safely and reliably in the real world over a long time, you might be able to argue it's proven in use. This could potentially allow you to reuse that component in a new design with less development effort because its real-world safety track record is already established.
So real-world experience counts as validation. That's fascinating.
It's a recognition that field performance is incredibly valuable data. So this whole field monitoring process includes decision-making, defining fixes like recalls, and reporting issues to everyone who needs to know, internally and externally. It's comprehensive.
Okay, beyond monitoring, what else happens during operation and service execution?
Well, there's the fundamental requirement for adherence to plans. All maintenance and repairs must follow the service plan and service instructions we talked about earlier. No improvising on safety procedures.
And documentation again?
Absolutely. Keeping records, paper or electronic, of what was done, when, ensuring traceability. For trucks and buses, this even covers formal processes for remanufacturing certain elements safely. And finally, part management continues to be critical. Supplying, storing, transporting spare parts according to the safety guidelines. You need the right part, handled correctly, to ensure a safe repair.
It really drives home that safety is this continuous thread woven through manufacturing, driving, servicing. But what about the absolute end, the scrapyard? Does functional safety still matter when a car is basically done?
It does. It might seem counterintuitive, but yes. The decommissioning phase, planned back in 5.4.3 and executed under Clause 7, still has functional safety considerations.
Right. What's the risk?
The main goal is ensuring the vehicle and its safety bits don't pose unreasonable risks to people dismantling it or to the environment. Think about EVs again.
High voltage batteries?
Exactly. Or undetonated airbags or seatbelt pretensioners. These are pyrotechnic devices. They contain explosive charges.
Right. You wouldn't want those going off accidentally during dismantling.
Precisely. So the standard requires decommissioning instructions. These tell dismantlers the specific steps and safety measures needed. The classic example is instructions for safely deactivating airbags before starting disassembly, or procedures for safely discharging or removing an EV battery pack.
So it's about making the car safe to be taken apart.
That's a great way to put it. The standard acknowledges decommissioning happens in phases before dismantling, during dismantling, after dismantling. Part 7 mainly focuses on the before and during phases, providing the instructions needed to make the vehicle safe initially and then how to take it apart safely, mitigating those immediate system hazards like airbags or high voltage. It ensures a safe end to the life cycle.
We've covered a huge amount of ground production, operations, service, decommissioning. It's clear these phases are way more complex and safety critical than many might think. But you hinted earlier there are some underlying activities, some foundational things that support safety across all these phases, the unseen threads.
Yes, exactly. They aren't distinct phases in Part 7, but they're absolutely essential supporting processes running throughout. They enable everything else we've discussed.
What's the most important one?
Arguably change management. This is covered in detail in Part 8, Clause 8, but its impact is felt everywhere in Part 7. Basically, any change to the product, its parts, its software, or even the processes for making it, servicing it, or decommissioning it must be managed under strict functional safety rules.
Any change.
Any change. A software update, a supplier changing a chip, tweaking an assembly line step, even rebuilding a truck. Every change carries potential risk.
How so?
Well, you could inadvertently introduce a new hazard or break an existing safety measure without realizing it. Robust change management forces you to assess the safety impact before making the change and put necessary controls in place.
So it prevents unintended consequences.
That's the goal. Proactive risk prevention for anything new or modified.
What other supporting activities are key?
Well, problem resolution and defect tracking are fundamental, even if not a specific clause in Part 7. It's implied everywhere. We saw it in production identifying process failures. We saw it in operation, the field monitoring process detecting issues.
Right.
When you find a problem, you need a rigorous process to fix it, understand why it happened, track the fix, and make sure it doesn't happen again. It's about learning from issues and ensuring safety is restored and maintained.
So change management and problem resolution are constantly working in the background.
Exactly. They are the crucial threads weaving through production, operation, service, decommissioning. They ensure safety isn't just achieved once, but it's sustained even when things change or go wrong in the real world. They make the whole system robust and adaptable.
Wow. Okay. This deep dive has definitely shifted my perspective. Functional safety isn't just about the initial shiny design and those crash test dummies. It's this continuous, incredibly detailed commitment through manufacturing, through every mile on the road, every service visit, right down to the very end. Understanding these later phases gives you a much, much deeper appreciation for what makes a vehicle truly safe over its whole life.
Absolutely. ISO26262-Part 7 gives the industry that essential framework. It's how you manage the risks that pop up after the design is done. It ensures safety remains a constant, verifiable reality throughout the entire life cycle. It's about building and maintaining trust, especially as vehicles get ever more complex.
It really is. So the next time you're out on the road, maybe take a second to consider that intricate web of safety systems working constantly, not just the airbags and brakes you know about, but the processes that built the car, the monitoring that watches for issues, the procedures that guide repairs, all working silently in the background. How might really understanding that continuous safety commitment change how you think about owning a car, or maybe the future of driving, especially with autonomous tech on the horizon? Something to think about.